One final quick note about chemical potential before I move on. I should have put this at the end of the last video, but for a pure substance, there's actually a pretty simple way to understand chemical potential. So we can write that for a pure substance, so chemical potential again is looking at the change in G with respect to the number of moles. That's the basic idea, holding temperature and pressure constant. And if we're thinking about a pure substance, we can say, well, G is equal to however many number of moles we have times the molar Gibbs energy, right? And this is something maybe we can look up or we can calculate. So if we take a partial derivative of G with respect to N, holding temperature and pressure constant, well, the derivative of N times G bar is just going to be G bar, right? Because G bar is a constant here. It's the molar value. It's a property of the substance. And so for a pure substance, the chemical potential is simply the molar Gibbs energy for that substance. So that's a pretty easy interpretation here of what chemical potential means. Now, this won't apply once we get to non-pure substances, but it's still a useful sort of starting point for understanding chemical potential. It's just Gibbs energy. It's just a way of looking at it while also thinking about changing the amount of the substance. So the molar Gibbs energy doesn't depend on the amount of substance you have, right? It just depends on it's a quantity that is a per mole thing. So it doesn't matter how much you have. So as you're making changes to your system in terms of number of moles, it's that molar value that matters. So even if you have more liquid than gas, right, there's just a bigger amount of it, the molar Gibbs energy is what matters, not the total Gibbs energy of the entire thing. So even if you have more liquid than gas, if the gas phase has a lower chemical potential, meaning a lower molar Gibbs energy, the system will go towards boiling, right? The liquid will go into the gas phase.